Hi, welcome to course Seaa 3243 Section 2 Theory of Structure. In this video, our group is going, which is group 2, is going to present about the report that relate to our case study with the topic of twisted beam. So let's get started. Okay, so let me start with the introduction of this case study. On a particular day, students were attending class as usual in a private school in Johor Bahru. Then suddenly, a student noticed there is an abnormal appearance of the beam that supports the floor above, and he informed the teacher right away. Then, a meeting was held immediately with the management team, the member of PIBG committee, and the technical expert to discuss the following issues. Finally, they reached an agreement where a consultant team were appointed to help in investigating the situation, and the consultant team then decided to install an appropriate number of small columns beneath the beams to serve as additional support and restraints. Okay, so let's move on to the objective of this case study. First of all, the first objective of this case study is to investigate the failure mode of the structure would be. Secondly, is to analyze the structure and propose a satisfactory structure design. And then the last one is to provide a recommendation for buildings that may be exposed to the same situations. Okay, so for the material and structural assessment of the structural steel, we all know that structural steel is considered one of the structural materials that are widely used in civil-related construction fields. And its function mainly is to resist a load without failure. But we all know that it is important to examine it to ensure its safety in the construction process. So there are a few stages in assessing the structure, which are the first stage is the preliminary evaluation. In this stage, the purpose is to identify the crucial or component or element of the building in order to remove any existing concern regarding its safety. This is done by compiling data about the structure from drawings and the design calculation, and also by conducting a site inspection and many more others. So the next stage, which is the stage 2, is about the detailed investigation. So the purpose of this stage is to undergo refined assessment for those members where safety cannot be guaranteed. This can be done by carrying quantitative inspection, for example, low-tech, non-destructive test methods. The third stage, which is the expert investigation. In this stage, an expert team should be called if the problem has large consequence in terms of risk or of cost with respect to a decisions. Further assessment should using specific tools, for example, the high-tech, non-destructive test methods. Okay, so the last stage, which is the stage 4, is about the remedial measures. In this stage, the purpose is to suggest action to establish a service structure that is suitable and has adequate safety. Okay, so let's move to the next part.
For non-destructive tests, there are two tests that we think it is suitable. First, visual inspection test. It is examined only with the human eye. Examination and testing methods with capabilities beyond eye inspection are needed to detect tiny and subsurface fractures and damages in defective welded connections. In this situation, from the visual inspection, it can be seen that the pins are twisted even though tie rods are mounted at every 1/3 of the span. Visual inspection must be done before, during, and after the solution. First, the engineers must clearly define the defect criteria of the beam, then standardize the inspection performance. After that, they must analyze visual defects such as the twisted beam and communicate the improvement measure. Finally, take a snap at day-by-day issues to define the difference or any problem occurring. Next, for the second destructive test, eddy current method. This method helps us check whether the beam surface has a crack while it is twisted. This approach can be used to find flaws in both conducting and non-conductive coatings. This earliest application of EC method were detecting corrosion, fractures, and other material flows. The eddy current technique works more quickly and need less surface preparation, which is suitable for our current situation. From the picture, we can see the eddy cores are positioned next to each other on the prop with this method. When put on the test component, a dynamic magnetic field is produced around the prop. The test piece centered on the prop experiences eddy current due to this magnetic field. The currents created on the test piece flow opposite to the current in the coil and oscillated in a circular pattern. Any fracture or discontinuities alter the amplitude and phase of the eddy current, which are formed at a certain magnitude and phase, indicating a defect.
Next, for this destructive test, we decided to choose tensile test and torsional test. So let us see the tensile test first. It is used to provide data properties about the ultimate tensile strength, yield strength, and the elasticity of the steel specimen. This tensile test measures the force required to break a specimen and the extent to which the specimen could elongate till its breaking point. Next, depending on whether the material is brittle, ductile, or has the characteristic of both, the ultimate tensile strength might not be the same as its breaking strength, because sometimes a specimen might be ductile when tested in the lab, but when it is placed in service, the material may change its behavior. So we can say that the environmental factors such as extreme heat or cold can change its material properties. Okay, so let us see for the torsional test. This test is used to identify the behavior of material when it is twisted or subjected to torsional forces as a result of applied moments that produce shear stress about the axis. The modulus of elasticity, yield shear strength, torsional fatigue life, ductility, ultimate shear strength, and the modulus of rupture in shear are the measured value in this torsional test. So when the steel is being manufactured, these measured values are very important because it can be used to replicate service condition and ensure the design quality of materials are made properly to prevent any failure. Moreover, in our case, these values are then used as a guide to design the structural steel that is subjected to moment by comparing maximum moment exerted to the beam with the lateral buckling resistance moment. So when the moment exerted on the beam exceeds the resistance limit, we can expect that the beam will fail in lateral buckling.
So by using the methods of visual inspections, you all can see the picture at the top right corners. It is obviously shows that the beam has been twisted to a critical conditions. Next one is the value that we obtain from the torsional test are compared with the actual beam loading conditions, and the exerted moment is greater than the torsional resistance values. Therefore, we can conclude that the beam is identified to fail in lateral torsional bucklings. Next one is the beam will be twisted when the compressed flange become unstable due to its compressed flange not being restrained and being subjected to flexural induced axial stresses. Okay? The failure can be caused by few factors such as the unrestrained length, support conditions, flexural and torsional rigidity, load patterns, beam profile, wrapping, and the last but not least, geometric and material imperfection. Okay? So from the testing, we can identify that the main cause to this failure is due to the beam unrestrained length, where the longer the span, the easier the beam to be failed in such a failures.
Hi, my name is Rajahan, and I will discuss on the calculation of structural design and analysis check. First, we are going to determine the structural steel properties for the steel UKB 356x171x51, and we are assume the steel grade is 275, and the length of the beam span is given 10 meter, and the given design load is 12 kN per meter square. Next, for the section classification, for the outstanding element and interleaved element is within the class 1 limit, therefore the beam section is classified as class 1 plastic. For the design load, from the dimension of the layout, we can calculate that the ratio is greater than 2, therefore it is a one-way load distribution. We convert the load to uniformly distributed load. The design load acting on the beam is 48 kN per meter. Next, we consider the beam is supported with 2 support, and we can determine that the beam is statically determinate. Since the moment calculated is 600 kN is greater than the critical moment, therefore the beam will be failed in these cases. Hence, we are considered to second cases, whereby the beam is supported with 2 support at the end and 1 column at the center. In these cases, based on the determinacy check, we can conclude that our beam is statically indeterminate to first degree, and the moment will be calculated based on the moment distribution method. Firstly, we are calculating for the distribution factor and the fixed end moment based on the cases. Next, we are using the table to distribute the moment. Since our beam is supported by pin support at the end, therefore the moment will be 0, and at the middle will be 150 kN based on the calculation. Next, we are proceeding to calculation on support reaction. For support, RA is equal to 90 kN, RB 300 kN, and RC 90 kN. Next, based on the reaction calculated, we can draw shear force diagram and the bending moment diagram. And the highest moment is 150 kN, and the critical moment is 349.19 kN. Since the moment is less than the critical moment, therefore the beam can cater the load and failure will not occur in these cases. Last but not least, we also calculate for the buckling capacity checking and the deflection checking. Since the buckling capacity we calculated is 172.35 kN, which is greater than the moment, therefore lateral torsional buckling resistance is adequate for the beam section. Since based on the deflection checking calculated, the allowable deflection is greater than the maximum deflection of the beam. Therefore, the deflection adequate for this beam. That's all for the calculation part. Thank you.
This is the planned layout of the structure and also the load distribution. So the design load given is in the aerial load. Therefore, the load is changed in terms of the line load. According to our analysis, a ratio of the long span to the short span is 2.5, which is greater than 2.0. Therefore, the loading will follow one-way load distribution, in which half of the width of the panel will transfer the load on the beam. Next, the beam to be selected to analyze is beam 2AB, because the loading transfer from the panels to beam is greater. Here we have few formula to check whether the beam is suitable or not, which is the lateral torsional buckling resistance, deflection, and also the critical bending moment. And the critical bending moment is assumed as the design resistance of the cross-section. There are two cases being considered. First case, simply supported beam without any restraint along the beam. Based on our calculation, we identify there is no redundancy and the reaction force can be solved by using three equilibrium equations. Furthermore, maximum moment is greater than the critical moment resistance of the beam for the 10-meter critical effective length. Thus, the calculation clearly shows that the beam is believed to have no enough resistance against the loading acting on it and the failure may occur. Second case, beam with supports at both ends and small column is placed underneath the beams. As in trial and error, we decided to install one column at a mid-span, 5 meters from each supports, and the beam now has becoming statically indeterminate to the first degree and cannot be solved by normal practice, which is the three equilibrium equations. Indeterminate structure can be analyzed using the unit load method, slope deflection method, and moment distribution method. The moment distribution method is chosen because it is easier, faster, and provide a quantitative solution and qualitative understanding of the structural behavior. Next, the critical effective length of the beam has now changed to 5 meters, and its maximum bending moment is less than critical bending moment, and the buckling moment resistance is also acceptable, as well as the deflection of the beam is also adequate because it is less than the allowable, and this shows that the beam is safe and have enough resistance against the loading. From these two cases, we can observe that the columns will act as an additional support and restraint to the beams, which reduce the unrestrained length of the beam and increase its resistance without failure. In this case, the beam fails mainly due to the beam unrestrained length factor. Longer beam span resulting in a higher tendency of the member to fail in a buckling failure. To increase the resistance towards this failure, the main criteria is the unrestrained length. Beam capacity can be increased by reducing the unrestrained length because the shorter span is more stiffer and stronger compared to the longer spanning beam. Finally, as a result, we propose to have only one additional column located at the center of the beam because it is sufficient to cater the loading based on our analysis. This proposal can keep the cost in a minimal as only one column provided and at the same time provide the sufficient resistance. Solution and recommendation to avoid such failure in the future. Main element to consider is the unrestrained length. First will be the introducing of the column between supports because it will act as an additional support and restraint to the beams. Next, instead of placing a few additional columns that might reduce the spaces available, we highly recommended to provide an intermediate beam as a bracing, where the effective critical length can be reduced and give more resistance to the beam. Besides, proper selection of the beam specifications such as section, grade, and sizes also one of the solution. There are two categories of steel section which are open section and closed section. Open section can be H section, I section, and T section, while closed section includes RHS, CHS, and SHS. Closed section is more recommended as the torsional and lateral stiffness is much more higher compared to the open section. Moreover, higher strength of the steel grade and bigger beam size can increase the steel strength, but it is not suitable in this case because the beam span is long and the unrestrained length of the beam remains the same and has the same tendency to fail.
Conclude structure assessment consists of 4 stages, which are preliminary evaluation, detailed investigation, and expert investigation, which include destructive and non-destructive tests, and finally followed by remedial measures. The expected failure mode is lateral torsional buckling and is caused by beam's unrestrained length. The lesson can be learned from such failure is that a simply supported beam with a longer span with the intermediate support have low load-bearing capacity and buckling resistance. Failure can happen suddenly without any warning sign when bending moment exceeds equal critical bending moment of cross-section. Lastly, for recommendation for buildings that may expose to the same situation could be the additional intermediate support. Intermediate beam as a bracing and beam specifications such as section, grade and size. That's all from us. Thank you.